Good evening, everyone. Uh, I would like to welcome you all to the fifth session of this lecture series on structural design of uh, highway bridges. And as usual, our sincere gratitude to Professor Tisan Jayasinghe for conducting these valuable knowledge sharing sessions. And further, I have a small notice for you all that we have arranged a participation certificate for all the participants. So that 80% of attendance will be counted from today's lecture onwards, and those who complete that will have the participation certificate. So for recording purpose, I would like to ask you all to rename your name with the membership number as well. Other than your name, you can add the membership number as well. So then it is easy for IESL to record the attendance. And yes, over to you, sir.
Right. So today we'll talk about a little more on reinforced concrete bridges. And so far I have explained the theory. And last time I explained how we can find the reinforcement as per the Euro code as well. And I will take photos and send it to Engineer Banuka so that he can share all my notes with you. So basically, I have the notes with me, the last two sets of notes, but I have to take some photos and send it to you. So I'll do that after the lecture. So I'm going to get the camera on. So first we look at. I'm going to share the screen. So this is the fifth lecture on our series. So far we have discussed briefly about the loading that we had and the HP loading, and then Euro specification and the kind of axles that you can place or single wheel loads, and the abnormal loading which can actually vary between 600 kilonewtons to 3600 kilonewtons, or 60 tons to 360 tons. Earlier it used to be 100 tons to 180 tons. Now you can see a bigger range is given. So depending on the type of highway that we are using, this type of bridges, you have to make the decision. And then we also looked at this particular concept where we go with precast members with the idea of minimizing the weight of the bridge, And we said we can go with this kind of precast sections, and these are the keys to ensure that it acts like continuous. It locks in very well when you are doing. This is in situ cast concrete. This is precast concrete. So basically the idea is precast concrete will adhere very well or lock into the in situ cast concrete, and the shape of the bridge is like this. And then we have some guidelines that we have worked out by performing a number of designs. Right. So we'll take one of these examples and see how a bridge can be constructed. And then to determine the amount of reinforcement, again, some charts have been developed. So today we see how we can make use of this type of information. And so basically, first, without worrying too much about the exact dimensions, we'll first look at the concept well. So the concept is, if you are going to do a bridge, you are going to design it for Eurocodes. I'll stop share for a moment, and I'm going to get the other note on concrete design. Right. So let's see the cover requirement. Okay, let's look at the concrete properties first. Now we have to make a decision. What is the strength of concrete? Now, so we have to make a decision. What's the strength of concrete? For that, we have to see where are we going to precast? Precast. Where are we going to perform the precasting operation? And here you can see cube strength 45, 50 is there, and the corresponding cylinder strength is 40. So cube strength is 50, FCU is 50, and FCK is 40. So if you look at some of the important properties, there is the mean strength, and this is the kind of tensile strengths are here, and then the elastic modulus is about 35. Elastic modulus is about 35, and the elongation, the maximum strain is 3.5. So basically, whatever the equations that we tried last time will be applicable. So last time we learned the method that Eurocode uses. So I'm going to use the same method, but I'm now trying to tell you how we approach the problem as a structural engineer who is going to design a reinforced concrete structure. And so based on all this information, now we have to see what are the cover requirements. So for that, I'm sure you are familiar with all these things now. Now we have to see what are the cover requirements. And you can see now this is XC3 is for concrete inside buildings with moderate or high air humidity. Now this is XC3 is the one that we generally use in buildings. And external concrete sheltered from rain, this may be applicable to bridges, but on the other hand, we can go for XC4. Right, XC4 is more stringent, and if you are using XC4 and design working life 100 years, so increase the class by 2, and here C4050 reduce the class by 1 because we are using C4050, and we are going to precast the members. So because when you are precasting, what is the difference between precasting and normal concreting operation? Normal concreting operation, we are going to walk on the reinforcement. Whereas in the case of precasting, we are not going to do any of those things. So which means it says increase the class by 2. Here it says reduce the class by 1 and 1. So which means we can use S4. And if you are using S4 for XC3, the cover requirement is 30 millimeters. 30 millimeters. Okay. So the cover requirement is 30 millimeters. Right. So let's see how this information can be used in a structural design. Let's see how this information can be used in a structural design. So I'm going to stop sharing now. Now let's say our cover requirement for S4 condition is 30, and what is applicable is also S4 because it says increase it by 2 because we are going to design a brick that is going to last 100 years. Then it says reduce by 1, reduce by 1. So which means when we are casting, we can actually, so we'll keep this in mind. We really don't know how we can use it so far. Now let's say we look at the arrangement that we are going to use. So basically, we'll have beams like this. So whether this is 300 or 350, you have to decide. And if you want, you can go up to 350. Otherwise, 300 also might work. But that all depends on the that all depends on the weight of the beam that you are going to cast, because you have to finally lift it up and place it. So you have to look at the capacity of the crane available for you. Now these days cranes are readily available, so we can assume that we are going to make use of a crane. Now, what is the most important parameter that we have decided? The most important parameter is what is this X? At which spacing we are going to have at which spacing we are going to have at which spacing we are going to have these beams. So that's another one important parameter. And let's say we are going to have a depth of about 600 millimeters. Right? This is a typical case. I'm trying to tell you how to think about it. Right? So now we have to think about the loading. Let's say, we are going to use BS 5400 part 1, part 2 loading of 1978. Because that's because I mean, we may not be doing this kind of bridge in a major highway, but it will be, I mean, we want a cost-effective bridge done. So we'll assume that this is going to be a normal road, and we are going to design a bridge to carry a load which is equal to 30 kilonewtons per meter per lane. Then we have to decide what is the width of the lane, and let's say we like to have 3.5 meters of lane. So I'm trying to tell you, show you a typical problem and how to think about it, right? So now we have to see. Now one option is we can have the beams at 1.75 meters. So that will give us a chance to have the road over this area, and then that will allow us to have the pedestrian pavement we have to make sure that we can accommodate the handrail. We have to have a curbstone, and we'll end up with something like 1.6 meters for the pedestrian pavement, and we can repeat the same thing on this side. This is one of these are reasonable arrangement, right? So let's say we like this arrangement, and we have decided to go with this particular arrangement. That means X is going to be 1.75 meters. Right? X is going to be 1.75 meters. So we can have another lane here, another pedestrian pavement. altogether 1.75 into 3 plus multiplied by 2. So, so the width is 1.75 into 6 approximately. So it's a 10.5 meter wide bridge. So it's good to have some pedestrian pavements on either side. So let's assume that we are going to have it because we are going to have a cost-effective solution. Then if you look at it, then we have to cast some panels. So the most important question is, what is the thickness of the panel? What is the thickness of the panel? What is the thickness of the panel? So that is the most important question. So when you look at the thickness of the panel, we know we need 30 millimeter cover to the reinforcement. And we might need 12 or 16 millimeter bars. So let's assume that we are going to get another 10 millimeter just to get some idea about the thickness of the panel. And so let's assume that we are going to end up with something like this. And then we have now here it's 40 millimeters. So if it is 40, we have to make sure that at least 90 to 100 millimeters is used for as the thickness of the panel. 90 to 100 millimeter has to be used as the thickness of the panel. So let's assume that we are going to use 90 millimeters. So it's going to be 90 millimeters. And I'm going to have a cover of 30. And let's assume we can go up to 20 millimeters. We might not need 20 millimeters, but let's assume that we are going up to that. So this distance to the centroid is 40. And here you get another 50 millimeters. Right. Now you can ask a question. In Eurocode, whatever the cover given by these guidelines that I have shown you, they say there should be another additional cover of 10 millimeter to allow for construction tolerance. Now, if you are going to precast, the question is, do you have to consider these construction tolerances? Answer is no, because we are keeping a cover of 30, and by using cover blocks of 30 millimeter, we can assure that this cover remains 30, and we are not going to do anything that will change the cover. So because of that reason, we don't have to use this 10 millimeter construction tolerance. But if you want, you can use 5 millimeters. Why? Because when you're casting, you might use a polythene sheet, and it might have few wrinkles, and because of all these minor variations, if you want, you can allow about 5 millimeter, and that's all you have to allow. So basically, instead of 30 millimeters, if you want, you can go for 35 millimeters. On the other hand, if you are going to cast on steel shutters with proper cover blocks, then you can go for 30 millimeters, right? So that's how we have to look at it. So I'm talking about the practical aspects, right, of working out the dimensions. So once you do that, so we are going to get these beams at 1.75 meters spacing. And then the next question you have is, what is the bearing you are going to have? What is the bearing? That means how much you need here. So minimum is 40 and you can go up to 50 millimeters. So if you are going to have 50 here and 50 here, then if this is 300, you are going to end up with 200 spacing here. That looks reasonable. That looks reasonable. And so you can see why we need 300 millimeter instead of 250. The reason is we have to make sure these precast members are kept. But the most important thing about these precast members is make sure when you are precasting, the reinforcement continues from this to this, end to end. Reinforcement continues from end to end. So don't have a situation where the reinforcement stops halfway through. So you cannot have a situation where, now these are the details that are important. Don't have a situation like that. That is detrimental, because we are not having the reinforcement continuous over to the beam. So must make sure the reinforcement is continuous. Now this is 90 millimeters, and we are going to complete the bridge with an overall thickness of 180 to 200 millimeters. So this can be another 90, or it can go up to 110 as well. That is your preference. But you have to again look at on what basis we get these dimensions, because here now we are going to have two types of links here. Two types of links. This is one link, and when you are casting, you can even have another link like this. You can have two links, and the idea of this link is it should go up, and we have to have 30 millimeter cover at this end. We have to ensure 30 millimeter cover at this end, because we can easily ensure 30 millimeter, right? So if you want, you can go for 35 millimeter there also. And this particular link can be 8 millimeter, right? 8 millimeter, that is to carry shear. And so in addition to that, we have to assure that we can place a reinforcement like that, right? So when you consider all that, let's work out the dimensions with an enlarged diagram. So here you get this green color line, and then you get 30 millimeter cover, and a reinforcement goes like this, and then there's at least a 12 millimeter reinforcement, and you might have something like another 12 millimeter reinforcement continue, 12 millimeter continue. So here you get 30 plus 8 plus 12 plus 12, so get 24, 38 plus 24, 62 millimeters. So it looks, so 62. So if you are going to lace 90, so the bottom of this reinforcement, we'll have 62. So we can see, if you are going for 90 or above, it may be okay. So which means you can have a diameter of, you can have a thickness of, overall thickness of 180 to 200, provided the precast panel is 90 millimeters. So this is how you will work out the details for the bridge. It's very important we get the details accurate. And today is 21st. 3, 20, 23, 1, 2. Right. So yeah, it's very important we get these details very carefully sorted out, because before you start the structural design, we must work out this. Okay. Now, once you work out these details, you can look at the guidelines that are given. So now let's look at the guidelines. So let's look at the guidelines given. So the guideline is, now let's say we are going for a 12-meter span. 12-meter span. So that is a 40 feet bridge. Not a small bridge. We are going for 12-meter span. We are going for 12-meter spans. And the size will be, size of the beam will be 650 by 300. 650 by 300. The guideline given is 650 by 300. And we are going to use it 650 by 300, and we are going to use it at 1.75 meter interval. And so we are going to have 50 millimeter bearing here. Here we are going to have 50, and we are going to have overall of 180, and these are cast at 90. Right. So you can see, I'll share the screen. Right, so you can see for 12-meter span, the size of the beam is 650 millimeters by 300. Right, 650 by 300. And so I'll stop share. So you can see 650 by 300 and 1.75 meter spacing. Right, and this will be loaded primarily by HA loading, right? Which means HA loading will be something like 30 divided by 3.5 equals 8.57 kilonewtons per meter square. 8.57 kilonewtons per meter. So once you work out those details, then what are the components that you are going to design? Number one, we are going to design this beam, the slab, precast slab. And what is the load? The load is the weight of concrete that you are going to place, and that is 90 millimeters thick concrete. And we have to think about the width of this member. So if you look at the width of the member, we prefer a width of 450 millimeters. You will ask why. Again, the answer is we are going to have 3 reinforcement, and we are going to maintain a distance of 150 millimeters. And then we are going to place the other panel next to it. There also we can have this. So if this is 450, here you get 75. On this side also you get 75. So similarly here you get 75. So which means it's like H12 at 150. So that's why we prefer this 450 millimeter width, because when you place the reinforcement, you can place the reinforcement at 150 center to center. But depending on the reinforcement requirement, you can change the diameter. Again, you will ask why 150. No, if you look at bridge engineers have been very comfortable with this 150 millimeter spacing for bridge decks. So it's something that they have developed traditionally. The reason is they actually look at the crack possibility for cracking. In reinforced concrete, the easiest way to minimize cracking is use small diameter bars, but a large number of small diameter bars than using small number of large diameter bars. So they like using small diameter bars like 12 millimeter at 150 to using 16 millimeter bars at 200. They prefer using small diameter bars at close space. That's the reason. So that's something that with experience they have noticed. When you are using small diameter bars, then you can actually improve the performance, because the chances for cracking would be minimal. So in that case, now this particular beam having a width of 0.45 meters. This is the load, and you have to multiply that load by 1.2 multiplied by 1.1. These are the factor of safety, gamma F, and this is called gamma F3. So there are two factors of safety, and I'm just talking about the BS loads. Right, later day I will explain the Eurocode loads, but because now today's aim is to make you understand the design philosophy for reinforced concrete. So I do not want to complicate it by introducing a new loading system. So basically the idea is this BS 5400 part 2 1978 loading system is very simple, very easy to understand. So basically we have to make sure that this top slab can be cast without needing any props, because in a bridge, it's difficult to provide a prop in the middle. So this is difficult. So we are not going to provide a prop in the middle. So with this, you can find the loading intensity, which is 0.09 is because of the 90 millimeter thickness, multiplied by 0.45, that is the width, multiplied by 25, will give you something like 1 kilonewton per meter. Multiplied by 1.2, multiplied by 1.1. So that gives about 1.33 kilonewtons per meter. So you can see it's a very small moment, and you can design it for bending moment is equal to W L squared by 8, which is given by 1.33 into we just assume that the span is about 1.6 meters, because here you can see the center to center is 1.75. So we say the span is 1.6 squared divided by 8, and that gives a very small moment, 1.33 into 1.6 squared divided by 8, and 4256 bending moment, and then you can find the reinforcement, and let's say that is AS1. Now what is the situation? So when you cast this, the slab will become continuous like this. And now we are going to apply the live load moments. And due to those live load moments, also you are going to get another bending moment. And for that, you can find the reinforcement AS2. So when you are providing, ensure that what is provided with AS1 and AS2, AS1 for dead or plus self-weight. So actually I have to consider the dead weight as well, self-weight also. So basically this will be doubled. So it should be not 3.66 because this has to carry the self-weight of the beam as well. So altogether it's 2.66. So it will be 8.4. So here I considered only the weight of concrete, but the self-weight is also there. So you have to consider both. So when you consider both, this will be should be multiplied by 2, and so you get 2.6. So this is dead plus self-weight of concrete plus AS2 is what you get, what you need to resist the bending moment in a continuous beam. So for the live loads, it is continuous, and you are applying a load equivalent to 8.57 kilonewtons per meter square, equivalent. These are the load, but equivalent, right? Okay. So for AS2, it is continuous, and AS1, it is simply supported. So that's the difference. So if it is continuous for AS2, then you have to make sure we have this situation, and we have this reinforcement, and this particular reinforcement is also provided. So here you get AS2, and here you get AS1 plus AS2. So whatever you get here, you can provide here as well. Why? Because there's a hogging moment. So you can actually calculate the hogging moment, and I say AS3, right? But AS3 will be pretty similar to AS2. And then, so you get this coming here. This, the other additional reinforcement provided that way. So you have to provide all these reinforcements. Why? For live loads, top slab could be continuous. You cannot say that it is perfectly continuous because these RC beam is also going to deflect a little bit. So because of that, it's not a perfect continuous situation, but we assume a perfect continuous situation, and we provide the reinforcement. So because we have a little bit of uncertainty, what is the method? So here and here. Here we get AS1 plus AS2, and be little generous here. In the span. Here you can get what is AS. Is that clear? Why we are going to be little generous here is we know beams are supporting the slab, and beams are also deflecting a little bit. Because of that reason, if the support settle, then you can't get the full effect of the support. So because of that reason, we will be little generous in the span, whereas we can be strict with the support reinforcement. So that is something that you have to keep in mind when you are deciding the final reinforcement, because there's only one way this slab bridge can fail. Where is it? It is at this. In this section, it can fail. And that failure occurs due to sagging moment. So the best way to resist sagging is be little generous with this particular reinforcement. So that's something you can keep in mind, right? So if you need only 10 millimeter, you will provide 12 millimeter. If you need 12 millimeter, you might consider providing something like at least a 16 millimeter bar in the middle. So here we are getting this situation. So the middle bar can be, you need only 12 millimeter, but middle bar you might provide 16 millimeter, and these can be 12 millimeter. So in that way, you are providing little extra reinforcement than the minimum you need. So that way, this will be very robust. But again, you have another problem. What is that? That is, when you are designing the top slab, you have to design it for a more rigorous situation. That is a 10 kilonewton, 100 kilonewton point load acting at the center. Point load acting at the center. So after designing for all those live loads, those are UDL. Now you have to check for this particular situation. Check for this particular situation. Now we have a problem because we are having panels like this. Each panel is 450, 450, 450. Now we are going to have a patch load. And what is the area of the patch? The load is 100 kilonewtons. The stress has to be 1.1 newtons per millimeter squared. So force divided by area is equal to stress. That means area is equal to force is 100 into 10 to the power 3 newtons divided by stress 1.1, and once you take the, so what you get is 100 to the power 3 divided by 1.1. So 90,909 millimeters squared, and take the square root of that area. So you can see the contact area of the load is 301 millimeter by 301. So it will need a contact area of 301 millimeter by 301. So you are going to get a patch load here. Now you have a problem because this huge load is going to act on one panel, one precast panel. So what you do is, we have done some load sharing because we are going to have a street concrete, and this concrete is there. So whatever the load will be distributed, though these panels are separate, the loads will be distributed. So we say this panel carry 40% of the load, this every 30%. So although you have to design for a 100 kilonewton load, you will design it only for a 40 kilonewton, 40% of the load or 40 kilonewton load acting at the center. It's very important. Otherwise, if you try to design for 100 kilonewton, you will find you need enormous amount of reinforcement in the in the top slab. So you have to always think how much load distribution could take place because we are going to have a number of panels side by side. And so we have done testing. We have looked at the load distribution. There are research papers published on Engineer Journal for this type of testing, covering this type of testing for precast panels. So our conclusion was, directly under the load, you can say 40% of the load is carried by the panel directly under the load, and remaining 2 panels will carry 30% each. Is that clear?
Yes, sir.
Right? Right. So that's it. So basically, we assume that it can carry. So because these are important things, because when you are designing the top slab, there are 2 conditions that you have to meet. One is you have to make sure all the UDS can be carried by the top slab. In addition to that, you have to make sure if there's a very heavy wheel load of 100 kilonewtons acting on a slab, that is 10 tons, then that load could be taken by the panels, or the reinforcement in the deck is sufficient to ensure that this type of heavy load will not cause the failure of the bridge, right? And again, when you are looking at this 100 kilonewtons, because we are checking it for ultimate limit state, you have to always apply the factors of safety for live load, and the factor of safety for live load in BS was 1.5 and 1.1. So 1.5 multiplied by 1.1 is 1.65. So you have to apply a factor of safety of 1.65 for whatever the load. But the most important thing is we are going to design it for only 40% of the total point load that we are going to apply on the slabs. So this way you can determine the reinforcement in the top slab, considering 2 different scenarios. First scenario is that it's subjected to the normal UDL, but the second scenario is it's subjected to a point, right? And there's some other load called knife edge load that will act simultaneously, so that it also has to be considered. So basically, first consider the live load scenario due to designing it for HA loading, and the chances that if you want, you can check it for 100-ton vehicle. That is, HB vehicle. So basically, in addition to that, you can consider that this bridge will be subjected to 25 tons of 25 units of HB B type loading, and giving a total weight of 100 tons in vehicle with 4 axles at 1.8 meter spacing, and this length can vary between 6 meters and so on. So it will be 6 meters in this particular case, and so you will end up with something like that, and each axle will carry 25 tons. That means each wheel will carry 6.25 tons each wheel. So the moment you look at the wheel load, now you know these 62.5 kilonewtons. If you have already designed the top slab for carrying 100 kilonewtons, then you might find that this 62.5 can be easily carried. So when you design for 100 ton, 10 ton wheel load, then the other loads will be generally okay. So this way we can make sure that The top slab is having a thickness of 180 millimeters, going up to 200 millimeters, depending on the kind of control you have. So you can actually make sure that we have these beams at 1.75 and the depth of the beam is 650. Depth of the precast beam is 650. And for 12 meters, we are going to get an overall thickness of about 830 to 850 millimeters. Right? 850 millimeters. And you can see it's not a small bridge. We are talking about 12 meters, which is equivalent to 40 feet span. And a stream having a width of 40 feet is a reasonably wide bridge, reasonably wide stream. So you can see we are going to have a bridge of reasonable length, not a very small bridge. So once you decide all those things, then we have to consider a situation for the beams. So again, we have two situations. So please civil engineering section committee number 6. Again, you have two situations. One is we are going to place, we have the beam, we have another beam, and we are going to place this, and we are going to place this concrete. So these 180 millimeters, and the weight is 0.18 into 0.45, 0.18 into 1 meter length into 25 into 1.2 into 1.1. So you get 0.18 into 1 into 25. 0.18 plus 1 meter length and multiplied by 1.75 meters. So this way you get 1.75 meters. 1.75 into 0.18 into 1 multiplied by 25 multiplied by 1.2 multiplied by 1.2. So you are going to get a beam simply supported at 12 meter span and carrying a load of 10.395 plus self weight. So let's assume that all that comes to 11 kilonewtons per meter. So WL squared of 8 is equal to 11 into 12 squared divided by 8. That is 11 into 12 squared divided by 8. 198 kilonewton meters. So it has to be designed to carry 198 kilonewton meters. For a 600 millimeter deep beam, it's not a major moment because last time we took an example of 600 by 300 beam as far as I can remember, and we ended up with a reinforcement. So for example, if I tell you the kind of reinforcement you need, it's about so what you need is about 1053 square millimeters. So I'm just done an approximate calculation. So you can see now you have a 600 millimeter deep beam. 650 millimeter deep beam, 300 wide, and you will need about 1,100 1,200 millimeters squared or 4H20. 4H20. You need something like 4H20. Now that is to ensure that this particular beam can carry the weight of the deck before any composite action comes into play. Before any composite action comes into play. Right. So that's something that you have to first we can identify. So we can say again the first situation, the reinforcement. Now we have to see how this bridge is going to behave when it is subjected to live loads. How it's going to behave when it's subjected to live loads. Right. So when subjected to live loads, what happens? Now this bridge, the whole structure is effective. So this will behave primarily as a flange beam, and this is 650. This is 180. And all this flange is going to go into compression. So this flange area will be in compression. So we'll have a flange beam having a shape like this. These 90 millimeters, and the width, the maximum width is 1.75 meters. There are some guidelines on the maximum width that you can use, but the maximum width is 1.675, but it could be slightly lower than that as well if you look at the shear lag effects. And then here you get 650, and the overall depth is 730, 830. Now the live loads are going to act on it. And if I approximately take the live load on that with a magnitude of 8.57 kilonewtons per meter squared, right? So the beam will now be subjected to 1.75 into 8.57 multiplied by 1.2 in 1.5 into 1.1. These are approximate values, but gives a good approximation. So you get 1.75 multiplied by 8.57 multiplied by 1.5 multiplied by 1.1. So you get 24.74 kilonewtons per meter. Now you can compare these two. Because earlier we have already considered the weight due to the weight of the panels plus beam as 11 kilonewtons per meter. Now you can say, see, we are designing it for a live load of 24.74 kilonewtons per meter, right? And then you can see if you take now again this beam is going to behave as simply supported. WS squared over 8 is equal to 24.74 into 12 squared divided by 8, and the answer is 24.74 multiplied by 144 divided by 8. So 445 kilonewton meters. So you can see because every 1.75 meters we are going to have a beam. So the load carried by a beam is whatever the live load that acts over 1.75 meters, right? So now we are going to get about 445 kilonewton meters, but we have an advantageous position now because we are having a beam of 830 millimeters of depth, and above all we are going to get a flange width of 1750 millimeters, and so effective depth of something like let's say 760, because here again you have to understand that we cannot provide, might have to provide an additional layer of reinforcement, so it will be like that. So because of that I'm going to consider D as something like 760 millimeters, right? So I have, because I have just kept some space, or I'll use a D of 750 millimeters, and this is going to be 90 millimeters. Now we have to see, now we know the moment, so I'm going to make use of the equation for calculating the so first we can calculate K is equal to M over F CK B D squared, and that is 445 into 10 to the power 6 divided by FCK is 40 multiplied by breadth 1750 multiplied by 750 squared, and we are going to end up with 445 to the power 6 divided by 40 divided by 1750 divided by 750. So you get 0.0113 less than 0.167. So which means we can singly reinforce the beam, and so singly reinforced beam is said is equal to D 0.5 plus square root of 0.25 minus K over 1.134. So Z is given by this equation. So the value of Z is equal to D 0.5 plus square root of 0.25 minus K over 1.134, and that is 750 multiplied by D multiplied by 0.5 plus square root of 0.25 minus 0.0113 divided by 1.134, and the answer is 0.0113 divided by 1.134 minus 0.25 minus 0.0113 divided by 1.134 square root plus 0.5. So Z is equal to 0.95D, and from this M is equal to 0.87 Fy AS multiplied by Z. So the bending moment is 445 into 10 to the power 6 equal to 0.87 Fy 500 multiplied by AS multiplied by 0.95 into 750. From this one, you can find the value of AS. That is 445 to the power 6 divided by 0.87 divided by 500 divided by 0.95 divided by 750, and you will get 1435, which means you will need something like 3 of H25, giving 490 into 3, 1470. Right. So now you can see, now we are going to have the beam 300 wide, 600 deep, 650 deep, having links like that, and one bottom layer of, or we can even change it, 4 numbers of H25 plus 3 numbers of H20. So I just change it. Instead of 4 numbers of H20 and 3 numbers of H25, I have provided 4 at the bottom, and I can provide 3 bars here. So that's the kind of reinforcement you let up. Right. So this way you can actually provide the reinforcement, and you can see this is a significant saving in the reinforcement, because you need a lot of reinforcement only in this particular beam to carry the loads. So the actual, because I have ignored some of the loads, so the chances are you might end up with 8H20. If you have considered all the loads accurately, because I have ignored some of the knife edge loads and so on. So if you have considered all the loads, you might end up with something like 8H25 in the beam. So if you look at the situation, is that you will have a bridge having a precast beam of 650 wide, 300 deep. And if you look at the weight of the precast beam, it's going to be 0.65 into 0.3 into 25. So it's about 5 kilonewtons per meter weight. The weight of the beam will be about 5 kilonewtons per meter. Weight of the beam will be about 5 kilonewtons per meter, right? And so that means 5 into 12 is 60 kilonewtons or 6 tons. So if you are going to lift the beam, you will need a crane of 6 tons. So if you can hire a 10-ton crane, then you should be able to manage it. And then we are going to have this, and the reinforcement will be like this. And this will be something like 8H25. Then you might need links, but when it comes to links, you are going to look at the shear force, and you can see that the total weight, total shear will be due to two different loads, and one load is like one load is about 12 kilonewtons per meter. So I think it will be about 11 plus the self weight. So it may be about 10.395 plus self weight of 5 kilonewtons per meter. So which is about 15.395 plus the other weight is the live load, and live load we calculated it as something like 24.75 kilonewtons per meter, right? So the total will be 24.75 plus 15.395. So the total is about 40 kilonewtons per meter. So now so we have a beam 12 meters of length and subjected to a load of 40 kilonewtons per meter, and so the shear force is going to be 0.5 times 40 multiplied by 12, or WL over 2, which gives 0.5 multiplied by 40 multiplied by 12, something like 240 kilonewtons, and that is, this page is 5, 6. This 7 and 8. Sectional Committee 7. Civil Engineering Sectional Committee 8. And here you get Civil Engineering Sectional Committee 9. Civil Engineering Section 9. And here you get 10. Right. Now you can see the shear force is about 240 kilonewtons, and we have a precast beam of 650 by 352 carried, because we might not consider this part, because we are going to cast it in two separate operations. So it will be conservative for us to consider that only the precast beam will carry all the shear force. So if you look at simple V, that is shear stress, that is 240 into 10 to the power 3 divided by 600 divided by 350. Simple V is equal to capital V over BD. And if you look at this particular value, you get 240 to the power 3 divided by 600 divided by 350, and the answer is 1.14. Simple V is 1.14, and you will find it's not a very significant shear stress. So it's a shear stress is very low, and that is the beauty of this method. Why? Because we are reducing the self weight as much as possible. We cannot do anything about lime, but what we do is we select sufficient number of beams at a reasonable spacing like 1.75. So each beam will carry only half the lay load. So this way we are keeping the weight of the bridge low, and each beam is carrying only half the live load per lane. So that way we are actually keeping the shear sufficiently low, and flexure is also sufficiently low. So the biggest advantage of this system is this one. Self weight is kept as low as possible. And in doing so, we are optimizing the structure to the level that it becomes fairly economical, because we have removed a huge penalty associated with self-weight. Self-weight is a huge penalty, and what we have done is, by going for discrete beams with a thin slab, we have minimized the amount of material in it. So the self-weight becomes as low as possible. We cannot do anything about the live load because it has already been specified. So because of this reason, we will end up with a fairly strong bridge, but the weight is as low as possible. So that is the philosophy behind this very cost-effective precast reinforced concrete beam slab bridge, right? So I have done some calculations, not all the calculations. I have shown you how the reinforcement can be calculated, and then I showed that the shear stress is also sufficiently low. So mostly you will find H8 links at 100 center to center would be sufficient at the close to the support, right? So the chances are you will find that H8 at 100 center to center would be very quite sufficient, and you can relax it to H8 at 150 center to center. Just do the calculation, and because with my experience I'm telling you that when you have V as 1.14, this particular detail works. H8 at 100 centimeter is quite sufficient, and then as you go beyond towards the center, you can relax it to H8 at 150. So this way we can actually reduce the amount of steel involved drastically, and because we are removing a lot of concrete from the structure, so we need less concrete. So otherwise we would have gone for about 700 millimeters of thickness. Now we have reduced it to about 180, and once in a while we get a beam. So you might get about 50% reduction in concrete weight, and the moment you do that, you get because now the loads are low, then the steel requirement is also go down, and we don't need foam work because we are going to precast all these. Only thing that we need is to hire a crane. That's all. And then we also have to think about HC 40, 50 concrete. And how you get C40, 50 concrete is by using about 450 kilograms of cementitious material. And I explained this method. And so you can go for about 350 kilograms of cement and about 100 kilograms of or 80 kilo, 260, about 270 and 80 kilograms of fly ash. So what is the reason? The reason is, you get very high degree of durability the moment you introduce fly ash. So if you look at the concrete mix for this particular bridge of C40, 50, so we say cement is 450, consisting of 370 cement and about 80 kilograms of fly ash, and then we get sand, aggregate, water, and wet density of about 2470, because we are using fly ash, the wet density will drop and the water content will go for about 160. And the moment you do all that, you get 2470 minus 160 minus 450, 1860 divided by 2.7. You will go for about 700 sand. And 1160 aggregates. And out of this, you will go for about 150 quarry dust and about 550 manufactured sand. And here you will go for about 160 chips and 510 millimeter and 520 millimeter. On the other hand, you can go for 20, 80 here and 20, 40, 40 here. So it's all up to you. You decide on the values. And so to ensure that you go for proper weigh batching, we can prepare separate weigh boxes for each item. And that way we can convert we use a density of 1.6 for 1.6, specific gravity of 1.6 for sand, 1.7 for aggregate, and 1.4 for cement, and 1.0 for water. So that way you can work out these are the densities. So density of cement is about 1,400 kilograms per meter cube, and sand will be about 1,600 kilograms per meter cube, and this will be about 1,700 kilograms per meter cube. So based on that, you can work out the volume of each item, and then you can ensure that we go for a curve. And civil engineer section. So we go for a curve like this, strength curve. So this is 40. This is 40. And we go for a curve like this. And we might actually say we need 40 megapascal cube strength at 28 days. Why? Because we have used fly ash, you know, with the time it will be 50 megapascal. So that way you can easily achieve a target. Otherwise, when you try to achieve 50 in 28 days, it may be hard. But we set a lower target of 40. Why? Because we are using about 15% fly ash. What happens? The strength development curve will go on. So by the time you complete the bridge, it would be of sufficient strength. And so basically you have to precast the beams early. And you also know, as far as the reinforcement is concerned, there isn't a huge difference between 40 megapascal and 50 megapascal when it is singly reinforced. But why we go for 50 megapascal is for durability. So by using fly ash with a later age, we can go for durability. Whereas at 28 days, even 40 megapascal is enough. Why? The reason is we know for sure for singly reinforced flange beams, the grade of concrete is not that important. If it is in 30 megapascal or above, even 40 megapascal, 50 megapascal, you are going to end up with the same mass. So you can do the calculations and see. That is with my experience. I know if the bending moments are not very significant, like in our case, then the concrete strength is also not important as long as you have 30 megapascal minimum. The reinforcement is not going to change drastically. So those are my experiences. So based on that, because always you have to do calculations and work out your own rules, so that just by looking at the numbers, you can say whether what are the important things about those numbers. So for example, we designed this flange beam for something like 445 kilonewton meters. And if you look at MOBD squared for this particular moment, you are going to end up with 445 to the power 6 divided by, we said 750 divided by 750 divided by 3 are 1750 is 0.45. It's a very small value. So because of that reason, it has a huge capacity, because this beam is going to behave as a flange beam for live loads. So because when you look at this number, strength of concrete is not important when you are deciding the amount of reinforcement. It's going to be the same amount, right? So likewise, I explained the full process involved, and I did few calculations to show you how the reinforcement can be calculated as well. And I also gave some guidelines on how to design for various live load situations, especially the point load that you get, and also how to select the cover condition. So basically, we looked at the basic numbers for the spacing. Then we looked at the cover requirement. And then we looked at the thickness of the top flange. And after that, we looked at, how we are going to arrange the reinforcement in each beam. And based on all that, we first understood how to calculate the reinforcement requirement in precast slabs. And then we also looked at the type of loading, especially this point load of 100 kilonewtons, which might govern the top slab design. And then we looked at the beam, and we said beam is going to be again loaded in 2 stages. For each stage, we calculate the reinforcement separately and add it up. And then I showed you the shear is not very critical, and we can make the assumption shear is going to be taken only by the precast section. And then I showed you how the grade of concrete can be looked at, and then why it's important to ensure the durability at a later stage, strength, while worrying only about the 28-day strength for the concrete strength when calculating the reinforcement. And I showed you that it is not actually governed by the strength of concrete. So as long as you have something about 30 megapascal, it's going to work. So that's the kind of the practical approach of designing a very cost-effective bridge by using high-strength reinforced concrete. So concrete is going to be high-strength concrete, like 50 megapascal or more with time, and we are going to use 500 megapascal reinforcement, but minimum amount of reinforcement, minimum amount of concrete, and doing so, a very lightweight bridge, but strong enough to carry HA and even HP 25 units of loading. And if you want a little higher loading, like 180 kilonewton HP loading, you might need a little more reinforcement. So with that, I can come to the end, and if you have any questions, I can ask. Any questions?
Yes, at the very beginning, there was a question, what is the basis for choosing 1.75 meter as the beam spacing?
So actually, I wanted to use 3.5 meter wide lanes for the vehicles. Because if you look at the type of vehicles that we use in our roads, our buses are 2.4 meters wide. Cars are 1.6 to 1.6 meters wide. So the dominating vehicle is bus. So if the bus is 2.4 meters wide, if you have only 3 meter lanes, then the lane is too narrow. So it's better to go for 3.5 meter wide lanes. So if you are going to have 3.5 meter wide lanes, it's better to have this beam spaced at 1.75 meter. Is that clear?
Yes. And
right?
there was another question. Could
Yeah.
you please recommend a book to refer on structural design of highway bridges under BS codes?
Under BS codes. Actually, Clark, the book by Clark, L.A. Clark, BS 5400 by L.A. Clark, right? L.A. Clark. It's a very famous book. It explains how BS 5400 has been derived. It's a fantastic book. It gives a lot of examples as well. One of the top, one of the best books ever written. Clark is a very well-known researcher who was associated with bridges. He has developed so many things in bridges. So yes, he had in-depth knowledge, and in his book, he has explained A to Z of how BS codes are derived. It's the best book. Okay. So for PT, I'm going to start next week. Right. So today is only RC. There will be longitudinal. Yeah. You are talking about interface. Somebody is talking about interface here. It's a valid question, but you can see we are providing these links at very close space. Interface here, you can see here we are having all these links at very close spacing. So we are having double links, this link and this link, and we are going to provide these links around 100 to 150 millimeter spacing. And the moment you do that, you find this interface here is very well looked after. Very well looked after, right? Here you get, here you get a weak plane, and the idea is, you need reinforcement to resist that particular interface shear. And so for this type of loading, because we are reducing the total bending moments, interface shear also becomes smaller. Is that clear? Because interface shear is applicable only for the live loads, not for the dead loads. Dead loads are not taken using interface shear. Interface shear is applicable only for live loads, so that's why we are actually extending this particular link. Right? I think, but you have to check it. There's no question, right? So fatigue is not a major problem when it comes to concrete. Fatigue will be a problem only for steel. Used to local analysis bridge particularly, right? So somebody has asked, how to analyze the slab for 100 kilonewton point load. You can certainly use finite element, but because we are casting the slab in 2 stages, we have done the load testing and found the ratios that you have to use for load sharing. Because finite element can't handle that problem. The reason is, if you have a thick slab, 200 or 180, cast in one operation, finite element works fine. But in our situation, we have a deck slab that is cast in two separate operations. So because of that reason, we have actually done load testing and worked out the reasonable values for load sharing. right? So, any other question?
It seems that's all, sir.
That's all, right? Okay.
And
Right.
I would like to invite
Yes.
Engineer Bashita to do the vote of thanks.
I'll be sending the Ashita. I'll send all the photos of the notes tomorrow. Right?
Yes, sir.
Okay,
Several
sir.
have asked about the notes also.
Yeah. So I'll be sending that, right?
Okay,
Because
sir.
I have carefully numbered all the pages, so I'll send all the notes by tomorrow morning.
Okay, thank
Okay?
you.
Right.
Thank you, sir. Yes, Bashita.
Thank you, Banduka. Dear attendees, I would like to extend a warm vote of thanks to everyone who made this webinar on the structural design of highway bridges possible. We are grateful to CESC for organizing this informative session and to the esteemed speaker, Professor Jai Singh, for sharing his valuable insights. I would also like to express my sincere gratitude to Engineer Kamala Gunawardena, the chairperson of CESC, for her support and encouragement. Our thanks also go out to the IESL Secretariat, Publicity Department, and IT team for their efforts in promoting and hosting this event. Finally, we are excited to announce that the next session of this webinar series will be held on next Tuesday. We hope to see you all there for another enlightening and informative session. Thank you all once again for your participation and support. Thank you.
Yeah. Can I also add a small thing? That is this coming Thursday, that is 23rd. We are going to have another discussion on related to a light rail transit project, where we are going to talk about mainly the application of Euro codes for improving the designs to end up with a slightly lower cost for the bridges and elevated sections of the LRT project. So because it's most likely that this project is going to happen soon, and there may be room for further improvement to the structural designs that have already been completed. The reason is already completed ones have been done according to BS 5400, whereas if we decide to go for Euro codes with higher strength materials, and also if we decide to use latest piling techniques and all that, there is a significant possibility for improving the designs and reducing the cost. So we are going to have a panel discussion on this particular topic on Thursday, that is 23rd, at IESL. Moderator is Dr. Devasurendra, who is a mechanical engineer, and Professor Anjit Disanayaka will also participate. So we are going to talk about various options that are available for us to consider, and we'll come up with some presentations on various aspects that can be useful. So if you are interested, please join that particular hybrid mode brainstorming session. Okay, panel discussion.
Okay, so I will share that flyer in our WhatsApp group.
Yeah. Yes. I saw the same flyer, but you'd better share it.
Okay, sir.
Right? Okay then.
Okay.
Right.
Thank you very much. Thank you, everyone. Good night.
Thank you, Professor. Thank you, everyone.
Thank you. Thank you very much.
Thank you very much.
Thank you. Thank you.